we can start right now. Okay, hello everyone. Welcome to our today's lecture. It's my pleasure to introduce Dr. John Martinez. He's one of the leading pioneers in the field of quantum computing. Dr. Martinez is a professor at the University of California, Santa Barbara, where he has been instrumental in advancing our understanding and development in superconducting qubits. With a PhD from UC Berkeley, Dr. Martins has also worked at notable institutions such as NASA's Jet Propulsion Laboratory. His groundbreaking research focuses on quantum information processing systems, particularly using superconducting circuits, and he has made tremendous strides in areas like quantum error correction and the development of scalable quantum processors. In recognition of his contributions, he was awarded the prestigious 2018 Breakthrough Prize in Fundamental Physics. Beyond his research, Dr. Martins remains actively involved in shaping the future of quantum technology. So please join me and welcome Dr. John M. Martins, where he's going to talk about today contrarying qubits using state-of-the-art fabrication tools. Welcome, Dr. John.
Yes, thank you much for the introduction and the invitation today. And I'm really excited to talk about maybe a new approach to making qubits. And the reason for this is there has been just a lot of progress in the field of superconducting qubits, a lot of different ways people are making it, lots of good ideas, steady progress. But in my view, as you look in the medium term and long term, where we want to make the qubits better and scale them up to maybe millions of qubits, we need to start thinking about things a little bit differently. In particular, the real problem here, I believe, in our thesis of my startup company, Colab, is that we have to make the devices better and more reliable and really use modern semiconductor tools to fabricate these qubits. So that's what I'm going to talk about today, is kind of the thinking behind that and where we think we're going to this. Now, I have a picture here of a modern semiconductor tool from Applied Material Cluster Tool. It's maybe about $100 million tool. This is really an expensive tool to get the state of the art. And this is very hard to do for academia or even a large company. But our business model at Colab is to collaborate with these kind of vendors who know how to build these kind of very sophisticated tools and work with them to put forth the most modern processes and tools and fabrication technology to build that. And we think by doing that, once we figure this all out properly, we're going to get the reliability and scale up capabilities we need. We're going to fix the materials coherence. And it's actually a good business case for doing that. I'm going to talk a little bit about where we are, and I'm going to talk about maybe academic research a little bit and complaining about it some and how we're approaching that, and also some recent results where we're using this philosophy of how to make better qubits, and I think we're making some progress in doing that. Now, in terms of thinking just about where we are in the field and whatever, I want to talk about the 4 big system engineering constraints. There's obviously many more than just these 4, but these are the ones you want to focus on. And first of all, in order to scale up and do something, useful, we really need to make qubits better. We are limited in scaling, not by the number of qubits we have, but by how good the qubits are. And for example, ion traps are very good. Superconducting qubits we need to make them better, though, in order to do what we want to do, both for error correction and for this kind of applications. And then, of course, you have to be able to make more qubits, and you want to make it scalability. You want to make sure your errors don't increase with number. And again, people are doing well with that, but we really want to have an eye towards how to make thousands, tens of thousands, millions of qubits. Two less obvious things to think about are connectivity. And obviously, the more connectivity the better you are. But even things like a cell phone, all the transistors are not connected to all the other transistors. And for example, in the surface code, you have a 4 connection per qubit. IBM heavy hex is about 2.5. Both can work. I think the Google is kind of interesting. Superconducting surface code, excuse, interesting because with more connections, you're a little bit more tolerant of dropouts. Note that atoms, for example, tend to have all-to-all, at least for small systems. And that's nice for NIST, but you don't necessarily need that for error correction. It may help you, but it's a system engineering optimization you have to think about it in terms of that. And finally, the one thing I want to mention is about speed. And, people often say, well, quantum computers are extremely powerful with the number of qubits, whatever. So maybe speed doesn't matter. Speed matters, okay? And when you actually think about running real algorithms, speed really does matter. It means what you can do and what you can't, but you have to run the numbers. And I'm just going to say that the real issue here is if you look at superconducting qubits or solid state qubits versus, say, atom qubits, it's not a little factor of 2 or 10. It's a factor of 1,000 or 10,000 or 100,000. It's a huge factor. And this really matters. Okay. Now, one thing I would say about this is superconducting qubits are fast. That's really great. But that actually puts a lot of constraints on controlling the system and how you build it, and it makes it more expensive. But as we've seen with regular computers, if you make something fast, that's really good, and you want to push in that direction. So though that's hard, it's a good problem to have. It's a problem I think we can solve. Now let's talk a little bit about reliability and scaling. And this is a plot of first the number of qubits versus time. This is a really simple diagram, too simple, but it's illustrative nevertheless, of the number of qubits versus time. Started with UCSB, we had 9. At quantum supremacy, we had 53. And then the Google group has recently done a quantum error correction at about 100 qubits. So they've been improving over time. But if you look at the rate of change, okay, that's fine. But what Google and other people, want to do is get to a large quantum computer by the end of the decade. And you see we're at a pretty small slope to get to 1 million qubits at the end of the decade. Okay. And I'm going to say this is, kind of not looking good. And by the way, Moore's law of an exponential growth versus time, that's a totally optimistic prediction. Okay, it may not be happening. So I like to think about this as a hockey stick, which is well known in economy and business. And the problem is not just the regular hockey stick, it's a hockey stick on a log plot. So it's an exponential of an exponential, okay? This is really hard to do, okay? And there's no obvious reason why this should work. Now, what I'm saying is our idea of going to this very sophisticated fabrication, I think might be the only solution for doing this. That's our thesis of our company. And that's what we're going to work on, because there's no hope of just plodding along at our current rate to get there. So we use modern semiconductor fabrication to get there. Let me just say beyond this is even if you have the fabrication, all this is hard to test because, it's hard to test superconducting qubits. You have to cool them down. It's not like you just wafer probe them, okay? So we need good models so that we really, really understand the physics of what we're doing here so that we can do relatively simple measurements and then kind of figure out if things are going to work properly. So there's a lot of things that have to be thought about differently in order to get this to work. Now, let me tell you what I think is a kind of a big problem in the field, at least in the academic end. I think some of the companies are taking this more seriously, but this is important to think about. And there's a big problem in our field is because what's the best qubits that people talk about kind of academically is based on reporting what has been called hero devices, but I'm going to say they're superhero devices in the sense that it's the best device in time, the best device on a chip, the best chip on the wafer, the best fabrication run, and a lot of times the best design. So you're not necessarily testing the materials. And then to top that all off, it's then often advertised in a blog post. So, you have a number, but you don't really know what to do. Now, all the fluctuations, there's huge fluctuations in this. And this is all known, it's TLS physics. We're going to talk about that. But given we know the physics, this is really not what you want to do. So if you want to quantify performance in a very serious way, what I call these superhero devices, it's nice, it shows the potential, but frankly, it's a little bit of hype. And we need to be more serious than that. So first of all, an average is a decent measure or median or however you want to do that. But I'm just going farther than that. It's well known when you build very complicated systems that you have to worry about the kryptonite. Okay, you have to worry about the things that go wrong. And that's a lot of times often what limits you. So from a system engineering point of view of building a complex system, it's the worst 1% of the devices that you kind of have to worry about too. Worry about too. So I'll talk a little bit about that as I go ahead and show some of our data. Okay, just to review, we're going to talk about scaling. We're hoping to getting with the good fabrication, but we have to go in, think about the models, how to improve the coherence, and very simply, just to understand things in general. Superconducting qubits are a nonlinear inductor capacitor resonator. And you could think about, well, okay, what's the loss in the inductance? What's the loss to the leads to it? And what's the loss to the capacitor? And the reason we're talking about superconductor qubits at all is you can kind of solve those problems. And in particular, what's interesting is for the inductor part and the Josephson junction part, superconductivity is really quite ideal because if you do things right, okay, you tend to get very, very low loss with that. And that's because if you use good superconductors, the right superconductors, you get a energy gap in the system. And that energy gap is typically, 10 times higher frequency than the qubits or resonators. And that gap protects you from dissipation, okay? And it can be crystal or amorphous materials. And the nice thing here is you can actually measure the imperfections such as quasi-particles, which may come from stray radiation, and can bound your loss. And we understand how to do that right now. So we still have to worry about it, but that's pretty good. In terms of circuits, you can get radiation, and that just comes from good circuit design and microwave engineering. And there's a lot of people been working on that, both in understanding how the radiation, the right designs, the right qubits, a lot of progress there. And still people are working on it. But that's a solvable problem. The last part is capacitors. And when you think about dielectric materials, okay, you say that, like even silicon, there's an energy gap of order in EV. So things work out really great where you don't have any states in the gap. But there's a problem there, and that is for real systems, which if you have crystals, the left-hand side's fine. But if you have amorphous materials with lots of random bonds to it, those get you states in the gap. And all through the gap, in the microwave regime, you get states there. And although the number of these defects are not necessarily very large, just say parts per million for what you care about, they have big dipole moments and they can give you a problem, okay? And you only see these at low temperature, so you have to study this very carefully. So the problem here is even though they're rare, they're big, and you can see them, and they have pretty high loss tangent. So you have to deal with it, and you have to design. Basically, you want to design your circuits without using any amorphous insulators in your system, and this is hard to do. This is very unusual fabrication issue, but it can be done. Okay. So here's just some data showing this and picture from the literature. The basic idea is in these amorphous materials have random bonds, and every once in a while, say you have an atom where it has two quasi-equilibrium positions, and it could tunnel back and forth here. And if it's at a microwave frequency that it tunnels, it can then be resonant with your qubit and absorb the energy. And these two-level systems studied for many years. You're just coupling your qubit to these two-level systems. And on the right is just an example of a parallel plate capacitor with SiO2 that we took a while ago, showing that the loss of that system for a typical amorphous oxide like SiO2 is in the 10 to minus 2, 10 to minus 3 region. If you go to high drive amplitude, you go to high temperature, you start driving a lot of transitions across there, and then you tend to saturate the TLS and not give you loss. And you can do other materials like silicon nitride, amorphous silicon. This gets better, but it's very hard to eliminate this from amorphous materials at all. So you have to deal with that. So just to talk about how we measure things, what we typically measure is not a parallel plate capacitor because the loss is too much, is to measure a coplanar resonator, which I've shown on the left, which is just a lambda over 4, two-dimensional coax, if you like. You form a resonance mode there. And then we bring a line near the top to probe it. And when you do that with a microwave network analyzer, when you're near resonance, it absorbs some of the energy in the line, and you get a shift in the transmission through there. And on the right-hand side, you plot the real and imaginary part of 1 over that transmission. And going from a low frequency to a high frequency, you trace a circle. And basically, you can take that circle and fit parameters to that to measure the loss, and then figure out how good that resonator is. So here's a sample of a test device that we make where you don't put down any amorphous insulators, and you can get Qs in the millions or so if you design it right, which is what we want to do to make good qubits. Now, the thing to realize, even though you're making it with no explicit amorphous oxide, there are, in fact, amorphous materials in this at the interfaces. So here's kind of a cross-section. Upper right, you can kind of see the cross-section of a feed line to the right and the coplanar resonator to the left. If you look at a cross-section, you have a substrate in blue, and then ground electrodes on the outside and a center electrode, and that forms the resonator. And all your TLS loss is coming from the surfaces. So in green, there's a metal substrate. In red, there's a substrate air. And in blue, there's a metal air. And all those contribute to the loss. Now, because most of the capacitance is going to the I dielectric constant of the substrate, turns out these interfaces have different contributions. And just very roughly, you can feel their relative contributions by the volumes weighted by the electric fields and the like. But the thing to remember is that the ratio between the blue metal surface to red surface air, green metal surface, red surface air, blue metal air is about 100 to 10 to 1. So the number's a little different, but that's the thing to remember. Your metal substrate is the most important because that's where all the capacitance is dominating in that. And that's the most important thing you need to worry about, then the surface air, and then the metal air, okay? And one thing to note is if you look at a good fraction of the papers talking about the surface losses right now, a good fraction, a little bit under 50% or so, I'm estimating, is talking about how to optimize the metal air. And this is the least important interface by a factor of 100. Now, sure, the data's there and there's a reason doing that. But, our view is to really system engineer this right. We have to go through and make sure that the biggest ones are the problem. Okay. Now, on the right here, I show some data of the resonator quality versus the measurement power. We do that. And what we find is that as you go to higher measurement power, it goes to higher Q because of the TLS saturation. Like we said before, it's shallower dependence, but it's still there. And then we see that as we go to very small widths of the center conductor, as seen in the upper right, as the width gets bigger, the Q gets bigger. And that's because if it's a surface effect, then surface effects always get less as you get to, bigger dimension devices because the surface becomes less and less of a fraction of what's going on. So by measuring this versus, let's say, width, you can then show that is it proportional to width in the right way and test what's going on. So this is how we kind of figure out what's going on here to some degree. Now, this is for aluminum here, what we did at UCSB more than 10 years ago. I want to talk about, so, how do you go about optimizing this? So in terms of getting the metal substrate, which is very important, people do cleaning of the surface and depositing that. We're trying to do that in a much more reliable way. And what's nice is if you look on the TEM of the right, of our reliable process, you can see that regular crystalline layers of silicon, and then on top of that, regular crystalline layers of aluminum on top, and you have an atomically sharp interface between the silicon and aluminum so that you're minimizing any amorphous material that can be there. And that's one of the things that we're really trying to optimize in what we're doing. Talking more about, materials and what we do, I want to highlight a very beautiful experiment that the Princeton group has done on tantalum on sapphire. And on the horizontal axis is the surface participation ratio. But I think the physical way to think about it is these are the gaps in these coplanar resonators on the left-hand side, where it's 2, 4, 6, 8, 10, 12, 16. So you get a bigger gaps, and then the resonator quality on the horizontal axis goes up, like I just showed you. And then they can also make some other bigger lump circuit things where the Q gets even better. And it shows that as you make the devices bigger, the loss gets less as you expect it. And it's really nice. It's many devices, it's showing surface loss. And one of the interesting things they do is that they clean the surface, both the metal surface, air surface, and the substrate air surface. And that goes into the blue data. And things improve by a factor of 2, a little bit more than 2 when you do so. Showing again that these interfaces are important. It's probably being the substrate air because that's more dominant. Now, I want to say there's a lot of people working on tantalum on silicon, tantalum on sapphire because of these very beautiful experiments. I do want to point out that if you look at the aluminum silicon resonators that we make all the time, very reliable, that looks like tantalum, the tantalum devices. Now, if we have look at our best aluminum silicon, which requires a little bit more work to do that, that gets to be comparable to the best tantalum on sapphire. So I don't think tantalum or sapphire is this magic material. Niobium is also known to be really good. Maybe sapphire is a better substrate because it's less prone to chemistry errors and processing. So, but there's still a lot of things to work on. It's good people are exploring this. But, all these materials are actually pretty good to use. One of the things I want to talk about is this surface loss has some interesting physics to it. And what you see when you look at the qubits depends on where the two level states are, okay? And what happens is there are large structures in your qubits where you have farther distances between the metals and the electric fields are going to be smaller, but they're going to be a large area. So like on the left here, think about the metal surfaces or the substrates in between the qubits. So it's almost a millimeter long, so it's a large area, a large distance. They're going to have low coupling to the TLS, but to be a lot of the coupling. And in that case, you're looking at many TL, small TLS, and the continuous loss tangent kind of model of that is the way to think about it. And it's going to kind of give you a background loss, okay? Now, as you go and focusing in, you start seeing structures, in this case in the middle, from the cross junctions. And the distances between the metals are smaller. This say right around the junction, a few microns. And that means you're going to have bigger electric fields. And that means you're going to couple more strongly to the two LSs. And in that case, you're going to, see the individual two level states, but there's not going to be very many of them. So for the left hand, it's spacing, it looks continuous. Here, you're going to see a few TLSs, but maybe a 50 megahertz spacing randomly be seen that, very roughly. And then you go to the actual junction to itself on the right-hand side, then the E field inside the junction is quite large. You would expect a large effect from a TLS, but it has such a small area when you do some computation, you don't expect to see it, or you see it very, very rarely. It's maybe 1 per 50 gigahertz, maybe even less than that. So most of the time you're not going to see it. It's statistically avoided. So these are the kinds of things you have to think about when understanding how these TLSs affect your qubit. Okay, so to kind of think about that and to do that, we wanted to show some coherence tests that we've done at University of Wisconsin, where Robert McDermott, a co-founder, is at. And what we're trying to do is make qubits. And we're using a two-layer fabrication. So we're doing aluminum or niobium. Niobium is good material too. Kind of base electrodes. And then we put Josephson junctions on top. And this is on silicon. And we're doing this in a way that is kind of breaking with tradition on how to make good qubits, okay? So first of all, we kind of think it's a practical design. So we're starting with the substrate that's silicon, and that kind of people commonly say sapphire is better than silicon. We have an island in material where people kind of think tantalum is better than niobium, better than aluminum. Okay, we're going to try aluminum. 1 and 2 junctions, people commonly think that 1 junction is better, but 2 junctions also. Differential and non-differential qubits, people worry about radiation. So for example, in the Princeton layouts of the qubits, they do differential. And we have some taper junctions that we know is a little bit better. And basically, our results are it works equally well for niobium aluminum, 1 and 2 junctions, differential and single-ended. So, there might be other constraints you have to worry about, but basically, all these different ideas work pretty well. And, we have to think about other things in terms of getting it. And there's a trend for longer T1 for larger gaps and tapering. So we tested them in this various ways. So we're kind of testing our model pretty well. So here's the data that we typically take. We call it swap spectroscopy. And what we do is basically measure the energy decay time versus frequency for a tunable qubit. So this is where you have 2 junctions, you put a magnetic flux, and as is normal squid behavior, that changes the effective critical current and increases the inductance with the magnetic field that lowers the frequency. So the way the experiment is done is shown on the bottom right, where we start in the ground state, we put a pi pulse to get into qubit 1 state, and then we quickly put in a flux in a few nanoseconds to change the frequency of the qubit. And then we let it sit there for some time, varying between, let's say a few microseconds all the way up to 400 microseconds or more. And we do that and then go back to the first point, and then we do a measurement to see if the qubit decayed. So we're basically measuring the qubit decay versus frequency to get the T1. And when you see that, there's a lot of green here, where the occupation is about a half, up to 150, 200 microseconds. So there's a lot of ranges where the T1 is pretty good. There are holes in this where it's blue right away, where it decays more quickly. And some of the holes are faster, and some are wider, and some are narrower. There's a big distribution. And this fixed the concept I talked about a few minutes ago, that the broad background is the TLSs kind of far away, and then you get a bunch of holes having to do with nearer leads, and where you get more T1 and the more holes. So it kind of follows that model with the spacing that kind of makes sense when you look at it more in detail. So given this data, you can then analyze it a little bit more. Oh, by the way, on the left, if you choose just the right frequency, to make your superhero device, okay, you can get a decay that's in the milliseconds. This happens to be about 740 microseconds. I think best is around 920 or so. But you can find places where you're statistically avoiding even the small TLSs, and it gets better. But what we like to do instead is just take all those T1s that we measure from that and then histogram them, okay, to kind of, there's some small and some big. Instead of a histogram, we do an integrated histogram or cumulative distribution, so that if you want to know the T1 at, let's say, 100 microseconds on the curve here, you go slide over to the left, and you see that 20% of the qubits have T1s lower than 100 microseconds, and 80% has higher. So that's the way to read it. And this is the way to look at what the distributions of everything is. And you see that the median here, or the average here, is about 200 microseconds. So this one was pretty good. Okay. Now, one thing we worry about here is we want the medium to be good, but we're worrying about this tail of the lowest T1 devices. And we want to make sure that, that makes sense and that's good. Because again, we're worried about whether the bad qubits are going to really screw us up. So what we can do, so what we do is we can plot this versus various devices. This happens to be aluminum. And then we have various untapered and tapered design. Taper seems to be a little bit better on average, a trend towards that. You can see a trend that as you make the gaps between the qubit capacitors bigger, then the T1 goes up as expected. It's not a perfect trend, but it does definitely trends. So that kind of makes sense. Again, you see these tails here. I want to talk about that. So when you look at the distribution, I'm putting it on a log scale because I'm worried about the few bad qubits with long T1 tails and how they can affect the performance of a big quantum computer. And what I'd like to show here in the University of Wisconsin data, which is the most clear, is at, in this case, above 1% or so. If you look at the blue distribution, okay, that's on a curve that's kind of predicted by a Gaussian distribution. For a cumulative distribution, it's an error function. It's pretty good. So you can, for most of it, you can describe as a Gaussian distribution, which given a random process you would expect. However, as you go to lower and lower probabilities here, then you tend to get a tail of that distribution. Okay, and that tail means that there's, let's say, an excess of qubits that have quite poor performance. Okay. Now, if you go to the left-hand series of curves, this is from several traces here from the Google devices, you see that you start, at the time they had lower coherence devices. The mean was about 20 microseconds or so. And they fixed that since then. It's pushed up a little bit like IBM's, a little bit like towards IBM's. You see that, but there's a tail there. And that tail starts at about 10% and has quite a large tail where the distribution goes down into a few microseconds, okay? And this means that, 10% of your devices, a few percent, 10% of your devices are not very good. And as you've looked into what happens when you make gates and errors in a big quantum computer, those kind of bad devices kind of hurt the system performance of the device. You really don't want to do that. Now, if you look at the orange data, which is pulled from an IBM device, which they show on the web, okay, and these are looking at the spread of the T1 devices. At the top, you see better T1s in about 100 microsecond or more, medium average. Has a Gaussian distribution, but it also has a tail starting at about a few percent or 10%. And it kind of looks like the Google curve just shifted to the right a little bit. Shifting to the right is good, but you have a tail there. So, again, that's better. And, they certainly know how to make good qubits. But one worries about those tails. And again, that's seen when you look at the errors of the system. What's interesting with the University of Wisconsin, where we tried to make a qubit, knowing the physics of the TLSs and coming up with a better way to put that all together. So there's a reason why we think it's better. We see that the T1s are pretty good. Again, these are much simpler devices than IBM, so it's hard to compare them directly. But when we make it right, we have a much narrower distribution, and that the tail starts at about 10 times lower and is about 10 times lower in width. So the bad qubits are much fewer. And again, if you're worried about 1% and thinking about that, we think this kind of fabrication might actually help you out a lot. Now, these fluctuations change in time, and this is the result that we had with, in fact, when I was at Google. And what this shows is that our T1s versus the qubit frequency, and then we scan it over and over versus time. So we take a color map of T1, and we see that these holes that you get, which we saw before, tend a lot of times stay in times, but they drift around a little bit, and sometimes they appear and disappear. And this is well known from TLS physics, that you're coupling to other lower frequency TLSs, and this is just changing the strain in the lattice over time, changing the T1. So this is a way to understand that. Now, in terms of actually operating the device, these fluctuations can force you to recalibrate, say 1 day to 1 hour. And these kind of bad qubits makes it harder to fit the algorithm. But the real problem is that if you start scaling up to more and more qubits, you have more and more qubits that can possibly go wrong. And you have to do faster and faster calibration. So you really want to try to get rid of this as much as you can so that you're not forced to recalibrate your devices. This is on the same color scale as on the left for this better qubits that we showed before. And you see that, okay, it's better everywhere. So that's helping you. If you just put it on rescale the color scale, you see kind of a similar kind of behavior as with the Google devices is very common for TLSs. But now the T1 scale is about 5 times bigger as before, as I showed that it was shifted. So you're still seeing drifts, but at least the scale is lower. Okay, I now want to kind of wrap up this and talk about some bigger issues. Here I want to talk about materials and coherence. And, how do we go about, making things better? When you think about how you do it academically, a common thread here is you want to make it as simple as possible in order to not introduce defects and problems and things that go wrong. Okay, and that's been the kind of the strategy, which has been good strategy, but that's not how CMOS succeeded and how you're successful in making very complex devices. So, one of the big things you want to do to make it more reliable and actually to give yourself more opportunities to make it better is to get rid of liftoff, which is what, all the junctions basically, or most all the junctions are made now. And this allows you to clean the interface and layer properly and use higher temperatures. And, you can do this in a cluster tool to not break vacuum. So there's a lot of interesting things you can do. The other thing I would say is as we go to applied materials and work with a professional foundry, it's amazing how easily they can optimize materials and do that very quickly. So, right now, the way we're making our qubits, even on 8-inch wafers, you're talking about 20-year-old tools. And if you're talking about liftoff, you're talking about 40 or 1960s era technology, okay, very old technology. And the interesting thing that we find is using like applied materials, we want to optimize a material, it can take a couple of weeks, which is mostly scheduling, by the way, instead of what would happen in 1 or 2 years in an academic situation. So you can really optimize things much better if you do that. And finally, before I wrap up here, talk a little bit about the business case, because doing this kind of thing is actually kind of hard from the business point of view. And if you want to use a 12-inch, you want to use the most modern tools. This is billions of dollars. Now, if you're making semiconductor devices, you're going to sell multi-billion dollars of product, you can do that. But this is absolutely not affordable for research. And if you just jump into a CMOS process, yeah, you can use it, but the tools aren't really optimized to do these crazy qubit processes. Okay. So what we liked about using Applied Materials is a tool builder. And they have a prototype foundry, but they're a tool builder. So the infrastructure already exists. They can reconfigure and test tools quickly for, say, millions of dollars and not hundreds of millions or billions of dollars. But of course, the most important thing is they have a great expertise in new processes. That's just kind of mind blowing to you. So, they're used to developing tools for a future foundry, and that's, kind of what we're doing. The other thing that I would say we're doing on the business side with CoLab is we have a horizontal business model. A vertical business model is, let's say, IBM in the 1960s, 70s, where they were building everything themselves and being quite successful at it. But eventually, people started to focus on their individual parts of it. So you have design houses and fab houses and packaging houses now. And that way, if we use a horizontal business model, we can share competencies and risks. And we think we can go much farther and faster by doing that. But this is all model dependent on good collaboration. So that's something we're really trying to figure out how to do well. Finally, just let me just summarize and make a few conclusions here. We think the qubits need to be improved in both quality and quantity. And, not, incremental, I don't think is going to get there. We need to have a big jump. And we think the big jump is to use the semiconductor tool superpower that we have in the United States and elsewhere. And that's going to be quite key in getting this to work. The second thing getting this to work is we're going to have models for what's going on. And I've kind of outlined a little bit about the TLS model that we use, that we pretty much understand what's going on. There's some things that are still kind of surprising here, but this TLS model tells us a lot. And this T1 measurement versus frequency is very useful. And we're studying a lot of things. So we think we have a good model that we can build on. And what's nice is as we've been thinking about this very carefully, and we're seeing improvements with advanced fab, better fab. It's consistent with the model. Still have a long way to go to figure out the optimal conditions and optimizing it. But I think we have all the tools right now to do that well. So yeah, I'm very excited about that possibility. And I think we can see some dramatic improvements in qubit quality and quantity in the future and really start to build even much more impressive systems that we're looking at now. So with that, thank you for attention, and I would be happy to answer any of your questions.
Thank you, Dr. John, for such an amazing lecture. We do have some questions. Okay, how do you see the future of quantum if these technologies are more complex to fabricate?
I think I can answer this in the maybe appropriate way. I
Okay.
think physicists are being a little bit naive about what it takes to build these very complex quantum computers. And it's amazing that we can build them at all and manipulate quantum systems, and that's right. But if you really want to beat a supercomputer, right? What, $100 million, billion-dollar data center using GPUs, that is really hard. And, we just have to get a lot more sophisticated in building our quantum computers in order to, beat classical computing. And, there's a bunch of different ideas people have, but if you want to get serious and compete about that, we all have to build things better, measure them better, push that. And that's really one of the big things that I'm trying to discuss here. I'm just talking about fab, but measurement, engineering, all this has to get better in our field.
Okay, which approach can we use to control the energy gap during the fabrication so it can be used as high coherence qubits?
So the question is the energy gap. And is this, I don't know whether that's the energy gap of the superconductor or of the qubit, but I can kind of answer that in general. Generally, you want the energy gap. Oh, okay, let's just start with the qubit. Um, we typically use a qubit frequency from 4 to 6 gigahertz or so. And that's, you want to go to a higher frequency so that it's easier to get into the quantum regime. Because you're comparing H bar omega with KT, okay? And you'd like to be able to operate at a higher temperature. But the real problem is as you go to too high of a frequency, then the microwave engineering gets really hard, really, really hard. And what's amazing is that at 4, 5, 6 gigahertz, you can kind of think of these as lump circuits. They're small enough to understand them in a fairly simple way and get it to work. Once you go above 5, 10, 20 gigahertz, it becomes a very difficult microwave engineering problem. You can probably build 1 or 2 qubits that way, but to build a big array is very hard. So, 4 to 6 gigahertz in a dilution refrigerator is kind of a sweet spot for that. What also helps you too is at 4 to 6 gigahertz, you can buy microwave components that are really cheap and easy to use. So your control electronics is simpler. If you go to higher frequencies, then the cost of that goes way up. And then the speed of the quantum computer would go up, and then that makes it hard. Now, one can also think about the gap of a superconductor, which basically says that you want the TC in frequency units being much bigger than the qubit frequency. And the nice thing is for aluminum, that's around 80, 100 gigahertz. It's way bigger than the 5 or 10 of that. You can do niobium and the gap's even bigger there, but it doesn't necessarily help you. And I'm going to say the superconductivity generally is not the problem, although you can certainly make mistakes there. It's usually the oxides or the superconducting metal oxides that are a problem. And that's more constraining you than the superconducting gap.
Okay, is there a need for improved quantum or classical theoretical models to better describe the relationship between the qubit design parameters and the probability of two-level systems occurring? Or is it just a material science problem?
Okay, yeah. What people have been doing since, we discovered these two-level states is building designs where you have a minimal of the surfaces. And, for example, in the 3D transmons, that's an example where you make the qubit very big, and then the E field to the surfaces becomes smaller. So that's an example of getting rid of that. And people also look at different examples. Like our particular design that I showed here is a way that we think that you can do that. So that's an active area of research. And then, yeah, but people have been working on that for a lot of times. And of course, every design has its pros or cons. So, we're not just trying to make one isolated qubit that's good. We're trying to make hundreds or thousands. So there's always a design push between this. And basically, if you want to scale up a qubit, you want to shield things and have more ground planes, and then your TLSs become worse. So you really have to do a very careful system design to figure that out. But people have been doing this for quite a few years, so there's a lot of techniques and ideas people use. But it's still an active area of research. We're still trying to figure this out better.
Okay, another question is the dielectric loss only the electronic dielectric loss as we are operating gigahertz, or should we consider other form of dielectric loss as well?
Yeah, so yes, there can be other dielectric loss in principle. I think the two-level states is what's dominating. However, when people make niobium qubits and they have niobium oxide on the surface, that seems to have a large loss tangent and seems a little bit too large than you typically would find for two-level states. So in that case, there's some other kind of loss that maybe people don't understand quite well yet, but there's something else that you have to worry about. So yeah, in those cases, it just could be little normal metal elements in there. One of niobium oxides is a normal metal, and so it's a very complex oxide. But yeah, when you think about these materials, you have to think about problems like that. And then lately, they've been studying loss, just the silicon substrate itself. And there seems to be some defect centers there that are TLS-like, but could give us loss also, that are a little bit different than the standard TLS of amorphous oxide. So this really needs to be studied some more.
Okay. Okay, why do holes exist at specific frequencies? Does it have to do anything with the resonance with qubit frequencies?
Uh,
Why do they exist at specific frequencies?
oh,
You
okay.
stated that they exist at specific frequencies.
Okay. Thank you. So what happens is
Okay.
you have a whole collection of random bonded silicon, and let's say silicon oxide, okay? And it's a rand, so you get a big spectrum of, different ways of bonds. And it means that when you have, where you have two quasi-equilibrium positions, uh, the frequency that it tunnels back and forth, it's exponentially dependent, say, on the distance that it's moving here. So with all these random bonds, you get a complete random distribution of all your frequencies. And you can develop simple models for with that, but it's basically due to the big randomness of these amorphous materials. You get all these different frequencies that kind of look like a continuous loss until you start seeing the discrete ones. When you look at defects in silicon, like the donors and acceptors, okay, those you expect to have discrete frequencies to it. But those are discrete because they're very low density. So you're basically putting a defect in a crystalline lattice so it can be predicted. But as soon as you put a defect into a random lattice, then then you just get a wide random distribution. I hope that answered the question.
Okay, other questions.
I'm sorry.
Okay, maybe I can ask another question. Okay. If two-level systems are inevitable and difficult to mitigate, can we coherently control them to our advantage? For example, could we design a novel qubit architecture that utilizes such back qubits to operate TLS effectively? Sure. That utilizes such back qubits to operate TLS effectively? Reverse engineering.
Yeah, that's a thought we've been having from the very beginning on, is there any control? And you can actually use these two-level states as qubits. Every once in a while, you get one that's pretty coherent and the like. But generally, it's just really hard to get rid of them. What you do at present is you have frequencies where the qubits work well, And you have frequencies where the qubits that don't work out, there's these holes in the T1. And you know, because of the random distribution, as I showed. And what we do is we tune the qubits to the frequencies where they work well. And then you can improve things, and just statistically, you can just avoid the bad qubits. So people have been we did that way back at UC Santa Barbara. We would measure that. We did that at Google. Continues to be done. So that's one of the advantages of using a tunable qubit, is that you can do that. So that's the games we play right now. And that works pretty well, and that gives you, you know, some factor of improvement. This is worth doing. Our particular view is that we really want to get rid of them to a larger extent. So that's what we've done, and where we think we've done. We have to take more data in the data I showed you from Wisconsin, where we think that's better. But you know, we feel confident that if we designed everything right, we can kind of get rid of these bad surfaces so that we can minimize the effect. We think there's more work to be done there. It's not like it's just designing your devices so they're kind of as far away from your metal as possible, or has the least effect as possible.
Okay, thank you so much, Dr. John, for such an amazing lecture. It was a really pleasure to meet with you. And thank you for taking the time to be in our program. Thank you so much.
Thank you. It's been my pleasure, and enjoyed all the share. Okay. Thank you. Bye-bye.
Thank you so much. Goodbye. Bye. Okay, hi, welcome.
Thank
Hi,
you.
Dr. Singh. Okay, Dr. Singh, welcome to our lecture today, to our session. Dr. Singh is an experimental physicist with research focused on quantum thermal effects and quantum computing. She received a PhD in physics from the Pennsylvania State University in 2012. Her PhD thesis was focused on quantum transport nanowires. She went to work at Sandia National Laboratories on quantum computing as a postdoctoral scholar. She's currently an associate professor in the Department of Physics at Colorado School of Mines. At Mines, her research projects include measurement of spin qubits in silicon, spin-orbit coupling in novel materials, and thermal effects in superconducting hybrids. She recently received the NSF Career Award and the Fulbright Nehru Professional and Academic Excellence Award. So that's a really great. So today the lecture is going to be about investigating quantum speed limits with superconducting qubits. So welcome, Doctor. Hi, Dr. Singh. Hi.
Hello. Thank you. Thank you for the kind introduction. And thank you, everybody, for being here.
Yeah, I can hear you fine. Yes,
Yeah, we could hear you.
Okay, great. Okay, so I'll get started. So I'm going to talk about my group's work on investigating quantum speed limits using superconducting qubits. In the background is a picture of the Colorado School of Mines. This is the physics department over there. And the work is also in this paper if you want to find out more details about what is happening here. So the supplemental information of this paper, for example, has a lot about the fabrication and the measurement setup and things like that, if people are interested in that. So the work was funded by the National Science Foundation and the Quaisnet Fellowship from DOE and NSF. And it was done as a collaboration between the Colorado School of Mines, which is my university, and the National Institute of Standards and Technologies in Boulder. Here are the people involved. So this was Dave Pappas's group from NIST. He is now at Rigetti Quantum Computing. So this group is no longer at NIST, but his postdocs, Mustafa and Junling, and his graduate student Tongyu helped with the measurements. then Jeshwan Gong's group at Mainz, his PhD student Alex and Casey, and undergrad students Bora and Kyle did all of the theoretical work that I'm going to talk about. And then finally, my group, my PhD student Joel Howard, has done all the measurements that I'm going to show you. And like I said, I want to acknowledge the NSF grant and the QuaisNet Fellowship for making this work possible. All right, so first of all, I want to start with what is a quantum speed limit. I don't know how much of a background various people in the audience have, so I will introduce many of the things which may be basic for some of you, but new to the others. So first of all, what is a quantum speed limit? And what is unique about quantum physics at all? So one of the things that many of us here have heard is this idea about a Schrodinger's cat, which can be alive or dead. That is one of the foundational principles of quantum mechanics. And from that comes the idea of a quantum speed limit, from the Heisenberg's uncertainty principle, basically. And quantum physics in the world today, of course, is everywhere. So it is the basis of basic devices which we are all used to, like transistors, etc. And there is also quantum 2 now, which focuses on uh, using entanglement, controlling entanglement, using quantum properties to generate new functionalities. So that is basically an overview of everything that is going on in the field right now. But coming back to the Heisenberg's uncertainty principle, we have all seen it stated as delta P times delta X is greater than h over 2 pi. And this is an excerpt from Heisenberg's original paper in 1927. This is one of the statements of the Heisenberg's uncertainty principle. This is the momentum position uncertainty. However, there was another statement in the paper, which is also taught in introductory quantum mechanics courses, which is an energy time uncertainty. So same statement, except the variables now are not position and momentum, they're energy and time. And although this first statement was accepted quite readily by the community and proved rigorously in the very next year, in 1928, this statement caused much more of a problem. And the problem is clear if you look at one of the variables. So time is actually not an observable in quantum mechanics. Position, momentum, and energy all are observables in quantum mechanics, but time is not. Time is special. And you can also see the statement, right? So he's talking about simultaneously. He's saying that you cannot measure position and momentum simultaneously with infinite accuracy, right? But when we start talking about energy and time, what does simultaneously even mean for time, right? So there was confusion about this, and one of the people who really did not like this second formulation of uncertainty principle was Einstein. And he actually came up with this Gedanken experiment, which shows that this cannot be interpreted as a measurement uncertainty. Like this does not mean that if you measure energy infinitely accurately, then time becomes uncertain. That's not what this means. And that is what this thought experiment is about. So there is a box, there is photons inside, you can weigh them. There is a timer control. This is a classical clock controlling a shutter, etc., etc. And if you go through this, you will see that you can violate this if you think of it in terms of a measurement uncertainty. Okay, so point being of all this is that this uncertainty principle is not the same as this. And the reason for that is that there is time in it. So then the question comes, what does that mean then? What is that delta E delta T is greater than h bar? And people started thinking of it as a speed limit. So that is where this quantum speed limit is coming from. So the first people to do that, this citation is from 1991, but the original paper, this is like more of a review paper. The original paper is from the 1940s, 1947, I think, from Mandelstam and Tam. And they were the first people to kind of interpret it as a speed limit. So they said that this, first of all, they rigorously derived this equation, which had not been derived before. Heisenberg had just done it as a plausibility argument. And then they said that the time that comes from this is tau quantum speed limit. This is a speed limit, and it sets a bound on how fast you can go from one quantum state to an orthogonal quantum state, right? And they framed that time, the minimum time. So they said that if you are in one quantum state and you want to go to another quantum state, you cannot do that infinitely fast. And they framed it in terms of the uncertainty in energy, which is this delta H over here in the denominator, right? So this was not fully accepted because there were some problems with this. Like the energy can be finite, while the uncertainty in energy is still infinite. So people did not quite like this formulation because it said that if the uncertainty in energy is infinite, then this quantum speed limit can go to zero. So Margolis and Levitin were the next set of people to look at this, with many in between, of course. And they said that this should not be delta H, this should be expectation value of H, right? And they said this is a speed limit, that is correct. The minimum time in which you can go from one quantum state to an orthogonal quantum state is given by this, is what they said. And then finally, the same Levitin and Toffoli put these two speed limits together, and they said that it is bound by whichever is bigger of these two, right? So this is the speed limit for a single quantum state evolving. And this is quite well established in experiments and people have seen it, right? So for example, and just so that you don't think that this is just math, which makes no difference in the real world, I have put together like the experimental implications of the speed limit, right? So for example, the speed limit sets a limit to how fast information communication can happen. And there's the citation for that. It sets a limit to how fast you can process information. So not just communicate, but also process. And then all kinds of other things. For example, the maximal rate of entropy production, the shortest time scale for quantum optimal control algorithms to converge, best precision in quantum metrology. And this is the one that most of us are familiar with. We have seen it somewhere or the other, the spectral form factor, right? So if you do spectroscopy on, I don't know, hydrogen atom or something, the lines that you get have finite width. They're never infinitely sharp. And that relates to the speed limit also. Okay, so basically it governs all kinds of things. For a single qubit, people have experimentally demonstrated it. Here's the paper for that. But for a single qubit, it's not that counterintuitive, right? For a single qubit, it stays, and I've started saying qubit now. I mean quantum system, right? For a single quantum system, it is not that surprising. It is saying that you cannot go from A to B infinitely fast unless you can harness infinite energy resources. So if you have a single qubit, if you can push it infinitely hard, if you can dump infinite energy into it, then you can go from state one to state two in zero time. And this just makes sense intuitively to most of us, right? But where this starts getting really interesting is when you start talking about two qubits and entanglement, right? So quick revision of what is entanglement. So most of us have seen it in introductory chemistry courses when we start talking about Pauli's exclusion principle, right? It says that if there are two electrons in the same energy level of an atom, if one of them is up, the other one has to be downspin, right? So these two are in an entangled state. That means one knows about the state of the other and acts accordingly, right? So they're sharing information. So I will not get more into entanglement, but just to link it to the concept that most people know. Okay, so then when we start talking about two quantum systems and speed limits in the context of two quantum systems, then what people care about is how fast can information travel between two quantum systems? How fast can you generate entanglement between two quantum systems, basically? And one of the initial people to look at it were Lieb and Robinson in 1972, and this led to they were looking at a chain of spins, and you perturb one of them, and you see how fast information propagates through the chain, and with the nearest neighbor coupling. And this leads to the Lieb and Robinson bound, which is quite common in quantum information nowadays. So they looked at it that way. And then more recently, so this is in 2002, Vidal and Hammerer and Sirac looked at it from the point of view of quantum computing specifically. So they said that if you want to entangle two particles, so that is the non-local gate. If you want a particle here and a particle there, you want to induce entanglement between them, then what is the time? What is the minimum resources that you will take? So This is the paper that is basically giving us the speed limit for entanglement generation. And they came up, okay. Okay, so they came up with a specific speed limit based on how strong your interaction between the two qubits is. And that is what we're going to look at experimentally, right? So before, this is the kind of the theoretical lay of the land. What is a speed limit? Why is there a speed limit? Things like that. And now I'm going to talk about what is motivating us to study it and exactly what we are going to do. Okay. So first of all, quantum states have finite lifetimes and coherence times. And you will see a lot in the literature out there on increasing those coherence times and lifetimes, right? So this is kind of an orthogonal direction where we are saying that let us increase the speed of the gates, right? The goal is the same, that within a lifetime, within a coherence time of a qubit, how many operations can you do? So that is kind of the quantum computing motivation, but there is also a fundamental physics motivation there, which is very interesting to my group specifically, and that is this. So in the theoretical paper that I just showed you, right, they have an analytical solution for two qubits. So they say that if you have two qubits and the coupling between them is GZ, this could be anything. For example, for superconducting qubits, this could be the capacitive coupling. Then the quantum speed limit time, so the minimum time for generating entanglement, is pi over 4GZ. Okay. Then for three qubits, if you add a third qubit to the mix, there is no analytical solution as of now, but there is a numerical solution. And in the numerical solution, you still have pi over 4GZ, but there is this additional term in front of it, which is 3 over 1 plus under roots square root 7, right? So this factor is less than 1. So what this is basically saying is that between two qubits, this is the speed limit. If you add a third qubit to the mix, the speed limit actually goes down, right? And this keeps going. So as you add more and more qubits to the mix, the condition being that each qubit has to talk to every other qubit, then you can see a speed limit decrease of the order of square root of n, right? So this is saying that as you get a fully entangled quantum computer, a two qubit gate will actually run faster than if you just had two qubits. So that is a very interesting prediction. And that is basically what we set out to see. So first of all, like I said, all of these speed limits are coming very much from math land. And there are assumptions like you can run single qubit gates infinitely fast. There are assumptions like you can turn couplings on and off at will, right? So our first motivation was to see how do these actually behave in a real quantum system, these two qubit speed limits. And then it is one thing to know that a speed limit exists. It is another thing to actually run a gate at that speed limit. So we wanted to develop an algorithm to actually generate entanglement at the speed limit. So that is what I'm going to talk about. So we focus on two qubit quantum speed limits for this talk. We have developed an algorithm to find the speed limit for a real two qubit system. And then we have tested it on experimentally. And then we have developed a software framework to automate multi-qubit chip design. This was before Qiskit Metal came along. So at that time, it was a new result. So in any case, let's get started with the algorithm. All right. So the algorithm works pretty much like any optimal control algorithm works. There is a new piece to it, which I will just talk about. So you know the Hamiltonian of the system. This is just your two qubits, and their Hamiltonian is given by H0. And the Hamiltonian of the gate that you're applying is H1. This gate is intended to take you to an entangled state. Okay. And you don't know what this H1 is. You want the algorithm to give you H1. That is the goal of this exercise, right? You know H0, you want to find H1, you know the initial state, and you know the final state that you want to get to. Okay, so the time evolution operator, which relates the initial state and the final state, is e to the IHT. Also, this is from foundational quantum mechanics courses, so you might have seen this before. And then all that we do is we split that time evolution operator into little steps like this. M steps specifically. And then we say that, you know, I was originally in state psi I, and I want to be in state psi f, and I want to find the overlap of the state that I end up in after applying U. So I'm in state psi I. After I apply U, I end up in state U psi I. I want to find the overlap of that state U psi I with the actual final state I want it to be in. So U psi I overlap with psi F. I want to find that number, right? And that is the fidelity that I'm interested in. There is a typo here. One side should be psi F. And then I can maximize that fidelity over M variables. And that will give me H1. So it'll give me this H. And since I know H0, I can subtract H0 from H to get H1. That is the goal, right? So finally, this algorithm will give me something like this. So it says 8 segments. That is this M that I chose. And it says, here's the amplitude of your drive that you have to apply to your qubit. And here's the time. So it basically tells me the drive that I have to apply to my qubit to take it from its initial state to the final state that I want to be in while maximizing this fidelity. Okay. So in this case, it has maximized this the infidelity, which is 1 minus fidelity, is 9.4 times 10 to the minus 5. All right. So normally when you do this optimization, let's say you use the library in Python to do optimal control, this tends to get stuck in local minima. And that is a standard problem of gradient descent type algorithms, right? So our algorithm has this extra piece, and that is this machine learning piece, which helps it to get out of local minima and have a better chance at finding a global minima. So that is the crux of the matter. This is what the algorithm is doing, and it is telling us a pulse sequence to run, basically, right? And when I say pulse sequence, this is basically just microwave radiation which we are applying to our qubits. This is its amplitude as a function of time. Okay, so because of this machine learning piece, this algorithm does better than grape and Q-tip, and it gets your result that will match your experiment better. So if you want to look at the algorithm, you can go to the paper that I referenced in the beginning, and it has links to it, etc., so that you can find it. All right. So in any case, we have the algorithm, and now we want to apply it to experiments on a 2-qubit system. So we start with, this is a picture of the 2-qubit device. This is not the one whose results I'm going to show, but it is also a device on the same chip. So the device was made at NIST. You can see the Josephson junctions here. The Josephson junctions are aluminum, aluminum oxide, aluminum. Everything else is superconducting niobium. And GZ is the capacitive coupling. So I showed you that the speed limit is pi over 4 GZ. That GZ is the capacitive coupling between the qubits. Okay, so this is a basic introduction to superconducting qubits. And I think I will skip over that given the rest of the talks that are happening here. So I'm sure you have seen this before. I'm going to skip it. There is a Josephson junction. There is enharmonic energy levels. So it is like a harmonic oscillator, but not quite, with a nonlinear element. There is state 0 and 1, and we are mostly concerned with 0 and 1. We are going to ignore the rest. We can represent these on a sphere like this. So I'm going to skip this slide completely because you've seen it before, and then move on to what our experimental system actually looks like. Okay, so our experimental system is capacitively coupled transmons. This is where they are. This is a zoom in picture. Again, those are the two Josephson junctions that we are interested in. They are coupled to readout resonators. So this zigzag line over here is a resonator, which is coupled to the qubit. And this line over here is where I'm putting input and getting output. There is fixed coupling between the two qubits. So nowadays there are many of these qubit chips which have tunable coupling. At the time when this experiment was done, like 3-4 years ago, we were still not able to get very reliable tunable couplers. So this particular chip has fixed coupling at 7 megahertz, and we did basic spectroscopy on it. And this is what the energy levels look like. And the lifetime is 40 microsecond and 21 microseconds for these two. And the T2 star time is 12 microseconds and 10 microseconds. So this is just basic characterization. And then this is how the measurements are done. And again, for those of you who are just starting in the field, there is a thesis from our group, which has this described in great detail, which you can look at. So basically, this is a resonator, and resonators are taught as in introductory physics courses. This is an LC circuit, basically. And then this is a qubit, which is also an LC circuit. Instead of L, it has a Josephson junction. And then this is the input and this is the output. And what we are doing is basically we are sending microwaves at the input and we are detecting them at the output, and we are sweeping the frequency. So that's what's on the x-axis. The frequency is being swept. And when the frequency of the microwaves gets in resonance with the frequency of the resonator, we get a big dip at the output. So that's what this is. So frequency changing, matches frequency of the resonator, and suddenly you see a dip, right? Now, the interesting thing is that because the resonator is coupled with the qubit, depending on the state of the qubit, this resonant frequency changes. So you will notice this 1 written there, right? This 1 is the state of the qubit. And if the state of the qubit is 0, the resonant frequency of the resonator is different. It'll shift like that. So just by sending microwaves here and sweeping the frequency, I can tell the state of the qubit. So this is an example of a readout mechanism for the qubit state. Okay, and this is what we are doing. So with that, we know we have an algorithm to take the qubits to the state that we want, and we have 2 qubits, and we have a way to read them out. So we are basically ready to do the experiment, and I will show you the results that we get. Okay, so the easiest thing to do is to find the speed limit between specific states, right? So I will say that I will start with a product state, down, and I want to go to a fully entangled state. An example of this by some measures is a Bell state. So I will say that I want to start here and I want to end up here. This is what I tell my algorithm. And I tell it that tell me the pulse sequence to get there, right? And it will give me something like that. Okay. So then I apply that, and whatever state I end up in, I measure that state and I measure its fidelity to the state that I want it to be in. Okay. So where is the speed in this, right? So this is basically what we are doing. So first I tell my algorithm that get me from this state to this state in 0 seconds, right? Here. So there's time on the x-axis. So I say that do this in 0 seconds. And of course, the algorithm can't do that, right? So your fidelity to your infidelity to your final state, which is 1 minus fidelity, is 1. That means you're not in the final state at all, which is what you would expect, right? How would you get there in 0 seconds? So then you say, okay, take a little bit more time and get me to that state. And the algorithm will try again and give you a best result. And you can try it, and your infidelity will be still high, right? 90% or something. And then you can keep giving it more and more time. And you will see that the minimum amount of time in which it can get you to this state with a fidelity of 1 is pi over 4gz, just like that analytical result said, right? So this is still just the algorithm. We have not run the experiment yet, right? But this is how we are going to get the speed limit. So then, oh, by the way, if there are questions, then I guess the moderator can stop me and ask. I'm happy to clarify as we go along. All right. So then this is the state speed limit, right? And it is important to do this, but it is not super interesting because in the context of quantum computing, you will not want to go to specific states. Instead, you will want to run specific gates, right? So what we also want to do is find the gate speed limit. And so to do that, you start with at least a full set of basis states. So your initial state is any of the basis states. And then you run the gate that you want to run. So this could be something like C naught, right? And then you end up in some state. And then you compare that to the state that you think you should be in, right? And you do this for all possible starting states. And then you find the fidelity of this. And to do that, you have to do something known as process tomography. It is, I think, beyond the scope of this talk um, to talk about why this is the fidelity, but it is summarized in this paper from 2002. And they talk about that if you do this, you start with an initial state, you run input poly operators, you run your actual operator, then you run your output poly operators, and you find the overlaps and you plot them in this matrix. You can put them in this formula and you will get a fidelity. And that is the fidelity that we are now going to plot on the y-axis, right? So by doing this, you can get the gate speed limit and following the same process that you give it more and more and more time and see how the fidelity improves, right? So we are going to do both of these. So first, let's look at the state speed limit. So we found an optimized gate using our algorithm to go from 0, 0 to this bell state, 0, 0 plus 1, 1 over square root 2. And we measured the fidelity of the resulting state to the desired state. And this is our result. This is the infidelity to the bell state, and this is the gate duration, right? So we also did this sanity check with the analytical theory that I showed you in the beginning of this talk. So the analytical theory, which assumes that you have infinite power drive, which means that you can do single qubit operations in 0 time, that will give you this green result. The theory that our theoretical model with the actual drive and the actual coupling between qubits, etc., taken into account, will give you this blue curve. And then the experiment gives you the orange curve, right? So on the y-axis is infidelity to the bell state. So how good of a job are you actually doing reaching the bell state? If you're doing a perfectly good job, then you'll be at 0. And on the x-axis is the gate duration. How long are you taking? And this is normalized to the analytical speed limit. So the analytical speed limit is 1 on this axis, right? And of course, the green curve is at the analytical speed limit. And our curve is our time is a little bit more than the analytical speed limit because our drive power is not infinite. Our coupling is not on-demand coupling. It is always on. So it is a little bit slower, but the experiment agrees with the theory very well, like you can see here, right? So given the experimental system that we do have, we are confident that this is the speed limit and that we are hitting it in the experiment. Okay, so then we go to the gate speed limit. And one of the most common gates that are used is a C naught. Um, it's kind of the counterpart of the NAND gate in classical computation, in the sense that just like if you have the NAND gate, you can generate any classical gate. So if you have the C naught and single qubit, C naught plus single qubit operations, you can generate any quantum operation. So that's why C naught is so popular. And we ran the C naught gate and found the fidelity using that formula that we saw before, which was called a simple formula. And this is infidelity as a function of gate duration. Blue is theory, our theory. Red, orange is our experiment. And green now is the agreement between experiment and theory. So if they agreed perfectly, green would be a straight line at 0. But it is very close to a straight line at 0, right? And you, of course, notice that the speed limit is more than the analytical speed limit. And again, this is the constraints of the system, that we do not have infinite drive power, for example, right? Now, we do want to check that if we did have more drive power, would we move closer to the analytical speed limit? So right now, the drive power is 7.5 megahertz. We increase it to 12 megahertz, and sure enough, we move closer to the analytical speed limit. We go 13.2% faster. So if we could push this to infinity, we would hit that one. So this is just a sanity check that we are talking about the same speed limit which the analytical derivations are talking about. Okay, and then another popular gate, because especially for superconducting qubits, because they have ZZ coupling, is the swap, and it swaps the state of 2 qubits. So we repeated the same experiment for a swap gate, and you can see the infidelity as a function of gate duration, and theory agrees pretty well with experiment. If you increase the drive power from 7.5 megahertz to 10 megahertz, the speed limit goes down. And there is an interesting feature here that I would like to point out. You will notice that the speed limit is actually less than the analytical speed limit. And that gave us a pause, because then you wonder what this is actually. So we think that this is coming from the fact that the the real things in the chip, for example, the always on coupling, that GZ that we cannot turn off, for example, is an advantage for some gates and it's a disadvantage for other gates. So for the case of the swap, we think the always on coupling is an advantage, and that's why it can get us faster than the analytical speed limit. The analytical speed limit does not have always on coupling, right? We are still looking into that. So this is work in progress. Okay. So then finally, I am going to talk to you about this software framework. So what we wanted to do, remember, I said that if you add more qubits to it, that speed limit goes down. So that is something that we wanted to check, that if you put in a third qubit, then what is the speed limit? At the time, it was not super easy to make 3 qubits with the same coupling between all 3 qubits, because that is what we would need for our algorithm. And so the PhD student that I told you about developed this software framework to automate multi-qubit chip design and extend our experiment to 3 qubits. Since then, Qiskit Metal is also out there, which does similar stuff. But this code is on GitHub, and it is very specifically targeted to designing multi-qubit chips. So it has less functionality, but perhaps an easier learning curve than Qiskit Metal. So it is called Qubit Simulation Module. It's on GitHub, and the paper has some information about how to use it. So you can look at that. And basically what it does is that you give it a device geometry. So you tell it that, this is my aluminum, this is my niobium, whatever you have. And it quantizes the circuit. It comes up with the spectrum that you will get, the coupling between everything. And if you don't like it, you say that I want to move these energy states apart. Let's say that you have some degeneracy which you want to get rid of. You tell it that, and then it'll iterate until it comes up with a layout that you do want. And the layout will be in K layout, and you can give it to a clean room, a fabrication facility, which can make that. So this is what we had at the time. And then we now have the 3 qubit chip, which is being measured. A little bit before I go to conclusions, a little bit about mines. So the Colorado School of Mines is the top national university and public school in Colorado, consistently in rankings across the years. We have an MS program in quantum engineering. We have some fellowships available. We have fully funded PhD programs in all STEM disciplines. Most STEM disciplines. And we also have certifications in quantum engineering. And we're always looking for highly motivated master's, PhD, and postdoc candidates. And if you want to work with us temporarily, there are also opportunities like the Fulbright Fellowship. And I was, like they said in the intro, I was on a Fulbright Fellowship to India recently, but there is Fulbright with other places also. So that is a way to come here for short-term projects, etc. All right. So to summarize what that experiment is all about, so we developed a machine learning inspired algorithm to find the fastest gate to go between 2 qubit states. So this is the time that our algorithm is taking divided by the analytical minimum time. This is the drive strength. So of course, when the drive strength becomes infinite, our algorithm and the analytical speed limit match at TF over TA min 1 is equal to 1. As the drive strength gets lower and lower to match real systems, the TF over T min starts to rise, but that is okay. It's not rising by much. And it is also showing you that if you can get the drive strength to be just 6 times of the coupling strength, which is not that terrible, you can hit almost the analytical speed limit. We have also shown that our algorithm with that extra machine learning bit can do better than GRAPE in QTIP, the gradient descent algorithm in the Python library, because that will stop converging as the drive strength gets bigger and bigger, because it gets stuck in these local minima, whereas our algorithm continues to converge as you keep increasing the drive strength. Then, so this is for to show that optimizing the gate speed limit is not something that happens. The gate time is not something that will happen just by the way. So this is a review of recent papers. This is the gate they are running. This is the year the paper is in. This is their fidelity of the 2 qubit gate. This is the time of the 2 qubit gate. This is the minimum time that they could take if And to find this, we need them to report the coupling strength, which they don't always report. So we might have excluded some papers from this. And then this is the ratio of the time they're actually taking to the minimum time that they could take. And you will see that it is far from 1. In some cases, it is as much as 11 times, right? So these gates are running much slower than they could. If you actively optimize for gate speed limit, so that's these last 3, this is our work, and you will see that our C0 swap and square root swap are all running very close to the speed limit. And it's only close and not at the speed limit because this is the speed limit given the experimental system. This is compared to the analytical speed limit. Okay, so this shows that this is a worthwhile thing to do. You can get your gates to run faster. Then we have experimentally demonstrated the speed limit using common gates at the common 2-qubit gates at nearly the fastest possible speed allowed by the interaction strength. So we have shown how this works on a real 2-qubit system. And then finally, we have developed this automation protocol to simulate and design multi-qubit chips. So with that, I would like to thank you for your time, and I would be happy to answer any questions.
Thank you very much, Professor Manakshi, for your such a great presentation. Actually, our moderator has some technical issues, so I will ask the questions to you. We have a few questions. First question is, why not we take a linear combination of H0 and H1, like a H0 plus BH1?
So that would just scale the amplitude strength, right? That would not change anything because that will just scale the amplitude of your microwave drive. So you could do that, but I don't see how it would help or hurt our cause either way.
Okay, thank you. Another question is, what is the mechanism we use to tuning the frequency of resonator and qubits so we can control the qubits to minimize the error?
Yeah. That's a good question. So I think typically we want the frequency of the qubit and the resonator to be close. So there is the measurement protocol that I was showing you. There is a specific measurement protocol for that, and you want the qubit frequency and the resonator frequency to be close but not exactly the same, so that they can interact but not interact very strongly. And there is well-known protocols for that. So I think in our case, the qubits are at like 5.2 gigahertz and the resonators are at 5 gigahertz, something like that.
Okay, thank you very much. Another question is, how does the speed limit energy time uncertainty fits into the picture of relativistic quantum mechanics, taking the relativistic space-time equivalence into account? Also, please clarify the limiting case entangled qubit in relativistic case.
Sorry. So how does this take into the relativistic speed limit into account, as in the speed of light?
Yeah.
Okay.
I can
And
repeat it if you
sure.
couldn't
Yeah.
understand. How does the speed limit energy time uncertainty fits into the picture of relativistic quantum mechanics, taking the relativistic space-time equivalence into account? Also, please clarify the limit in case entangled qubit in relativistic case.
So I think that speed is not related to this directly, because we are talking about the interaction propagating in terms of like using a capacitive coupling or an inductive coupling. So it is not the speed of light which is kind of governing it here. So we are talking about the Lieb-Robinson bound it here. So we are talking about the Lieb-Robinson bound. I am also unsure what does entangled qubit in relativistic case mean. So I'm not sure. I have to think about that.
Okay, thank you very much. Another question is, why we need high drive limit power?
Okay, so for like we saw in that single qubit case, right? So to get from one 2-qubit state to the other qubit state, you are going to run some combination of single qubit gates and double qubit gates. Those single qubit gates run faster and faster the harder you drive. Like we saw for the single qubit speed limit, right? The tau was inversely proportional to 1/h. So if you can drive infinitely hard, you can run those single qubit gates infinitely fast. Basically, that's it.
Okay, thank you. A last question is, can one do noise characterization with the difference between analytical limit and the experimental speed limits? Can you explain how G being ON can make swap gates show smaller limit experimentally?
Okay, so there's two parts, right? How can one do noise characterization? Noise of what? I'm unsure. I'm not sure I understand the question. So noise characterization with the difference between analytical speed limit and experimental speed limits.
Yeah.
Okay, I'm unsure about that. For the second part, can you explain how?
Second part, can you explain how G being ON can make swap gates will show smaller limit experimentally?
Yeah, totally. So the reason we think that is because this capacitive coupling already on, the native interaction between these two qubits is the ZZ interaction. And that coupling always being on means that that ZZ interaction is always on. And the swap gate is native to the ZZ interaction. So we think it is supporting the swap operation. In addition to our microwave drive strength, that G always being on is also supporting the swap.
Okay, actually have another question, I think, but okay, the question is same, I think, with others. Okay, today, thank you very much, Professor Manakshi, for your presentation and your time. That was great presentation, really. Thank you very much.
Yeah, thank you for inviting me, and thank you for all the interesting questions.
Thank you for answering all questions.